what was the thing about the average classification not always has vectors? So wait, against one bin to classify, we're gonna have to use weights, can't we? Yeah. So he wants to use that effectively. Yeah. Which is thick. Because one bin we need a specific weight.
We can still do weights, right? Because that makes us able to scale, right? We sort of weights in SRAM. That means we can.
Well, I guess yeah. We will be one bin.
At the moment, I don't know what the weights are. I'm in the centroid thing, where I get the centroid of the high energy and compare it to gradients of weight, not centroid, but gradient mass, and see the comparisons from where it came from. That just means oh, like right, left. Yeah. That's just very weird. Because I don't have adequate. Just get working through numbers. But that's just the last stage that I need to figure out. For both parts, we don't have it working for.
All right. Let's see. I'm gonna get started. So, thanks for making it. I know the weather is a little crazy out there. We also had a fire alarm in E2 right before this for a brief few minutes. So, did anyone see hail today? Or it was hailing on the east side at least. So, okay, we're gonna go over static timing. I have my laptop for a demo partway through, but I also want to talk briefly about the midterm grades. I posted this in Slack. I posted an original one. This one had some of the regrades, but it didn't have the regrades from the last hour. There's a lot of people submitting regrades that are just getting denied because they're wrong. Make sure you understand the solutions and what you did and so on, and don't submit a regrade that's not right. We're not going to let you submit multiple regrades per problem. If someone keeps doing that, I'm just going to say no. People try to, I don't know, abuse the system. So, but if there's a mistake, we will fix it. We will get the correct answer. There were a couple of them already. I think the layers in the last one, Hodder and I miscommunicated on labeling materials versus layers. So we fixed that. There was another one that had a slight error. We fixed that. And so yeah, if there's something that's legit unfairly graded, let us know. We'll fix it. The rubric is listed in Canvas or in GradeScope. So if you go in there, you can see why you got the points or not. We're following that rubric. If you don't agree with the rubric, then that's not a regrade. That's what we did for everybody, and we have to regrade everybody with the same rubric. So, but in terms of this, what really concerns me about this is just a little bit of, if you're down in this range, you should be pretty worried here. You should be very worried. I will say, though, that I looked through this, and most of the people in this, at least the left two bars, didn't submit the homeworks for credit, or at least one of the homeworks for credit. So these are people that likely did not even look at the homeworks before, try to do them before the exam. So that goes back to my try to do the homeworks before you do the exam. I looked at a bunch of other people. I think, in general, a lot of these people kind of lightly did the homework. They at least did it. Maybe they didn't try a lot because it's not graded. I don't know if they went over the homeworks again to see if they could do them with the answers, but that's one thing I would suggest you do. Overall, I thought that this exam was easier than past exams because I didn't have a curveball question on it, really. Most of the questions were similar to the homework examples, and so I think that shows that so many people did do quite well. Like all these people over here did very well, that it was a reasonable exam. So right now, the average is kind of low, but I think it's low because it's this weird bimodal distribution, right? The people way down and the people kind of in the middle. If we ignore that, the average is actually not so bad. Now, what I'm going to wait. I'm not curving this at all right now because some people basically got full points, quite a few people. What we'll do is improve on midterm 2, which is next week, and then depending on how people do there, we'll see if there's any sort of alternatives. But yeah, there's no real curve on this right now, no extra points. I was debating adding 10 points, but I'm not going to right now do something until after midterm 2. So again, if you're above the mean, you might need to study more. You might need to kind of revisit stuff, but I think you could be okay. Now, if you're on this other part, I'm going to encourage you go back and watch lectures, revisit the homework. Come talk to Hodder or I in office hours. That's not a problem, but you need to put in some of the work yourself first. Like I don't like meeting with people on an exam where they're like, "What can I do better?" I'm like, "Well, what did you do?" "Oh, I didn't do anything." Like, go over the exam and see what you did wrong. Like, try it. And so that's an important thing. That's how you learn, right? You correct things that you make mistakes on. I'm going to add that I think you should treat the homeworks almost like the exam. I should have said this from the start. Like, try to do it like an exam with your note sheet, or at least a light slide usage, right? Because then you're trying to do it and synthesize the knowledge on your own, which is what you have to do during exams. So that's another kind of important point. Now, homework or midterm 2 is next week. It is not cumulative. So I've never had a midterm 2 in this class. This is the first year, so I don't have an average grade. It's about the same length as the midterm 1, and it covers the next 2 homeworks. I think it's like 3 and 4, and that's lectures roughly 7 through 12 through Tuesday. So this lecture and the next one. It's not covering the prior stuff, but the final exam will be cumulative over everything. So this is just the second part. Focus on the things right now, and then revisit some of the stuff for the final exam. Are there any questions about this or midterm 2 for right now? Yeah.
So we only said 1, 3, and 4.
And 5. Sorry, we have one coming out right away. It's going to come out today. Yeah, that one is also included. That one is static timing. So the one you just did is gate sizing. The one we're going to release, we were reviewing kind of the problems and solutions, is static timing, and that'll be due. I might push it to Tuesday also to give you a full week, but it's going to be on the midterm. So yeah, thank you for clarifying that. I did all these homeworks. I created them all in December, so I'm trying to remember what was on them when I created them. So it's part of teaching 2 classes. You have to prepare so far ahead. Okay. Yeah. So that's announcements on this. Any more questions? No. Okay. All right. So let's go back to the static timing analysis. So we went over a lot of stuff, how it works. How did it work, right? It's an O(n) algorithm. That's the key thing. Linear time algorithm, meaning you only have to visit every gate or every pin on every gate 1 time, or 2 times, but 1 pass forward, 1 pass backwards. That's the key. That's how it runs fast. That's how it can be used for optimization stuff. If it didn't do that, it would be very problematic. Under the hood, you need to understand conceptually how it works. There's a lot of data that gets pushed around. I do have one problem on the next homework that's probably a little crazy because I kind of do some tables for the lookup tables and the static timing. You have to look at the tables and figure out which value and so on. But it's more tractable than looking at the real lib files. And my intent is you can kind of put together the delay models with the static timing. Now, in practice, though, you typically use a tool to do this for you, but you have to understand how it works, understand your decisions on setting up constraints and querying the tool for results. So at the end of last time, we basically mentioned a few commands for the static timing tool. You can define the clocks. There could be more than 1 clock, by the way. But you use this command called create clock. It creates a clock with a given period. It can have a Dewey cycle to it. If you create more than 1 clock, you can also specify that they are related to each other. If the edges are aligned but the frequencies are different, you can specify that. So this is just an example with a single clock, but you can do a multi-clock design, and you want to pay attention to how you define those clocks. Now, that's useful because that defines all of your timing constraints between flip-flops to flip-flops, right? You have your launching clock for the launching flip-flop, your capturing clock for the capturing flip-flop. Could you pay attention, or at least keep the talking to a minimum? keep it talking to a minimum. So that defines your flop-to-flop paths. Now you may also have primary inputs to flip-flops, and there's a special command called input set input delay, which specifies a delay relative to the clock, but it specifies kind of an off-chip delay before it gets to the input of your chip. So that's how you count for signals coming from somewhere else. And then similarly, there's a set output delay, which does the same thing. So as soon as your signal leaves a chip, it says it has to go to another chip through some logic on the other chip before it gets to a register. So these are trying to define the external conditions to your chip. Or if you have a module and there's other places on chip that signals come from and go to, it may be that. Like you do STA on one module and another module separately, you want to make sure that the input delay of the one matches the output delay of the other. Otherwise, you could have a timing violation. And then also for the inputs, you can specify the driving cell. So we know that adding load to an input will slow down the drive of that input, and that's what that accounts for. So otherwise you'd say, oh, just load all my inputs with a bunch of capacitance and long wires because if they have infinite drive, they'll be like really fast, right? This prevents that from happening. So it basically means you have to have optimized capacitance on your inputs. Same thing for the outputs. This load sets a capacitive load on output and says we're going to allocate at least that amount of capacitance for every output for the off-chip trace and the loads on the other design. So same idea. Okay, so I'm going to talk about a couple things, and then I'm going to do the demo. And I want to talk about these first just to so I'll use some of them in the demo. Now, one thing I kind of ignored in most of the examples was the transition times or the slew rates. But we know that wires and gates have different slew rates. We know that that affects their delay. These are propagated with the delays. Remember, we do rise and fall delays separately, and then we also do early and late separately. And then we have those 4 values for the delays, and then those 4 values for the transitions as well. So it's always a delay and transition pair, or arrival time and transition pair on a wire for all those 4 conditions. Now, the challenge is static timing it's an approximation. If you want to do something more accurate, you'd run SPICE, but SPICE is too slow, and you don't know what input patterns to do. But there's a big question of how do you propagate slew? Now, I'm going to give an example of what I mean. Most tools have an option of how you define this, and it changes the behavior slightly. For example, if you have 2 signals arriving at the same time, here's an example. 2 signals arriving at the same time, one option is to say the latest arriving signal here, its slew rate will propagate to determine the downstream stuff. Another option is to say, well, maybe I want the worst slew, because in this case, B, because it's such a bad signal, may technically arrive a little bit earlier than A, but it may actually determine the worst case delay of whatever this is going into. So assuming the latest signal has the slew we want to use is not correct. But it can be pessimistic to pick the worst slew among all the inputs, and so you don't want to do that either. So that's where it's a little tricky, and there's different options, and kind of even options between these two that you can set in the tool, and it'll give you slightly different delay modeling. Now, the reason that this doesn't matter that much is usually when you do static timing, it's pessimistic already. I mean, you're doing the worst path already. You're making a lot of bad, assumptions about all the delays and everything that pessimism adds up, and you're already conservative. So sometimes these things don't matter ultimately. The common case is going to be much faster than your bounds usually, but you don't want to have a failure in those bounds. Now, there's other delay assumptions too. How do we characterize the delay tables in the lib file? Well, if we had an AND gate, we assumed that the A input was switching and the B input was constant. That's a single input switching assumption for all delay models. That's actually a bad assumption. The worst assumption is as we had actually a problem on the exam, all the inputs were 1, so that all of the pull down paths were on at the same time in that AOI gate on the exam. And that would actually be the fastest case in that case, right? All of them pull down at the same time. And so you can have multiple input switching that change the behavior of a circuit. But we assume it's one at a time, and the other inputs are in the worst configuration to slow the output of the gate. And so this can lead to different slews, and it could add internal gate capacitance to the output, which slows down the gate. The other thing is that single input switching is an assumption. It is a necessary assumption because you can't do static analysis where you assume the worst of all inputs with considering input switching, right? It's counterintuitive. By doing static patterns of all possible values, you're saying that I have to ignore this. There's been papers on how to do it. I would say if you really want to push static timing, what they do is they say run static timing, and then you can actually save your SPICE netlist of your critical path, and you can actually have the inside input switch to see how it affects your path. Actually, OpenSTA, the tool we use, has that option to do that. And actually, I don't even know if most commercial tools do. At least it's not easily usable, but it's a way of kind of verifying things like this. You can go in there and say, well, what if I didn't have my side input switching? Or I did. You can see how it affects your critical path. The other assumption is the single input ramp. We know that signals don't look like a ramp. They're not this nice kind of, I don't know what you call it, ramp, constant ramp. When we simulated stuff, it was more like this, right? So it's more of a kind of quadratic charge and then approach an asymptote. That changes the behavior. We've seen cases, for example, where because of a slow input signal, you can actually have a negative delay in a gate because the slow input transition is so slow that the output finishes before the input finishes transitioning. That's an example of an extreme case of really bad slews. You can also have things like noise. If we talked briefly in interconnect about coupling noise to adjacent wires, you could have something like this where you overshoot, and then it comes back to a value because of coupling noise. That is not modeled in any of the delay models. But you may see it when you run a SPICE simulation. And so all of these things can cause problems. You may have, let's say we have a gate here. You have a combination of both of these. Like what if we have this signal's transitioning, and then over on this other one we have a glitch of noise that causes the signal to go down just a little bit and causes a blip because of coupling noise. It doesn't actually change that other input, but there's a kind of a dip on it while the other one's transitioning. And if those overlap, that can affect the delay of the circuit. So that is also not modeled in static timing typically. So now we're going to talk also about this, and I want to talk about these because I go over some examples of these as well. Because we're doing the worst case path and we're doing it in a static way, there's actually an opportunity for what's called a false path. And there's a few different ways that this arises, but basically it's a path that can never be logically sensitized. So it can't happen. It seems like it's the longest path in your design, but it can't happen. And in order for this to happen, you have to have fan out and reconvergence. If you don't have reconvergence, it typically won't happen. Now here's an example where if we set this input to 1, 1 in this case for an AND and NAND gate is what we call a non-controlling value. What does that mean? Well, if we set the input to 1, we don't know the output of the gate until we know the other input, right? If that y is 1, this first bottom NAND gate, we don't know what the value of a is. We have to know it's actually going to depend on x. If x is 1, then a is going to be 0. If x is 0, it's going to be 1, right? So that's a non-controlling value. So in this case, we know that this equals x bar. And then if we go through here, let's say that this is also a 1. Then we know that that's the non-controlling value, so this propagates through. Let me change the color. Because this is non-controlling, this propagates through. Now this one is also a 1, so that means that this also propagates through. And then we know that here, b is equal to x. right? It was inverted because of the first NAND gate, and it was inverted again because of the second NAND gate. Yes?
Will this happen in practice because those NAND gates are effectively inversions, so like you'll be wasting gates?
This happens frequently in practice. The reason being, it's the way you save area is you typically have fan out to reuse things, and then they get combined in reconvergence to, and maybe think about it in a K map. You draw a Carnot map, things overlap. Those overlapping parts are this. So if you have two minterms that overlap, it's exactly this. And so it always happens. You may have a big of a minterm as possible to kind of minimize the number of literals or the size of a gate, but then if it gets as big as possible, it overlaps with other minterms quite a bit. And so that does this. That's with two-level circuits. It happens even more with multi-level circuits. Yeah, that's a very good question. So these two inputs are non-controlling values, but what do they produce here? We know that the output of this gate is now a 0, because both inputs are 1, which forces the output to 0. Right? But neither of those ones were controlling value, but now that's a 0. Now that is a controlling value for this gate, which means that this path will never happen, because that's a 0. This output is always going to be 1, actually, because of this. So whenever I have that condition, that those two inputs set, that we have a false path. But if you use static timing, it's going to say, oh, my path from X to A to B to Z is the worst path. But it doesn't happen. So it's pessimistic. Now, what happens when you do this? Well, there are modes of static timing tools called sign-off modes, where they can do false path pruning. Now, what does it do with false path pruning? It takes your false path and enumerates your critical paths and says, can this happen? And it literally looks at the inputs and says, is there a possible way to sensitize this path, considering that my inputs could be anything? There might be a reset signal that's always low that prevents something from propagating, or an enable signal that's only in a test mode that never happens. Now, the problem is, it has to do that proof for every path. Now that's where it's no longer a linear time algorithm, doing a forward propagation, backward propagation. You're at first enumerating paths. There could be exponentially many paths. If you think about multiplier, there's many, many paths through multiplier if it's on your critical path. And then for each path, you're proving it can happen. So it's a proof within your enumeration of paths. So they do use that, but that can add a lot of runtime and verification time to your design. Yeah. So this is one of the issues with this. So this is a logical false path. There's actually another case where it commonly happens, which is in shared bidirectional buses. Most people are working on memories in this for like 127 projects, right? The common paradigm is to have CPU A, CPU B, and they go to a shared memory. And you use the same bus for writes as reads to reuse the data wires, let's say. Now, what happens here is, if this is a shared memory, basically you're saying, oh, if A can write to the memory, it can also read from the memory. Now, B can write to the memory and also read from the memory. But unless you implement a snooping protocol, these typically don't read and write from each other. Right? You're not going to have CPU B write to CPU A, or CPU A write to CPU B. Exception being, if you have a snooping protocol where you actually snoop the cache in the other one, then that might happen. But in the common case, it doesn't. And so you could see if the side of the bus on the CPU side is really slow, let's say, the read and write from that would be slower than going to the memory. So that would be a false path. Now, this also, you have to prove that it happens, right? So it has to go back into logic, and it would have to show that all of those paths in the memory bus can't be sensitized. And then it's a false path. Instead, what a designer says is, I know the spec. I know that this is a snooping bus. I'm going to say A can't write B and B can't write A. I'm going to run the command that just says, don't consider this. What we ran into a lot of times in prior classes is people would say, oh, I have this path. I don't think it can happen. I'm going to set a false path. If you're wrong, your chip's broke, right? Because if you're suddenly ignoring some paths, and then that's your critical path, your chip doesn't work. So you don't want to use this lightly, and you want to be extra careful that you know what you're doing when you do this. It's that well-known thing of garbage in, garbage out. If you set up your design with garbage commands, you're not going to get a realistic result. So that's something to be aware of. You have to know things about your design and what it models. There's other types of false paths. For example, you can have inputs to a chip that don't happen. Maybe you have 2 bits that specify 3 operating modes. Well, that other operating mode doesn't exist. It's unspecified what happens. If that causes a false path, that could be a problem. But you need to tell the static timer that these 2 inputs will never be high at the same time. And from there, it can then get rid of some of these false paths. Because otherwise, it's going to assume when it does this proving that any possibility can happen. Another one is you may have some states of your finite state machine that are not used. They're invalid states. So it's not only your inputs to the chip, but it's your current state of the chip that can have invalid conditions that can never happen. Think about this: when you write Verilog code, we like to write one hot, right? It's easy to decode, it's easy to read. There's many, many invalid states. Any 2 bits as 1 are invalid. So if any of those causes a critical path, then that's a false path. And then you can basically use a command like this to modify the timing constraints. So you can specify a path with a from and to argument, and you give it basically instances of flip-flops or inputs and outputs. You can also do a false path through a signal. So like if you have a bus, you can say anything that goes through this is a false path maybe. But this is where if you can use wildcards too, and the asterisk to match all names, that's where it gets dangerous. And so yeah, this is one of the things that you can do for these false paths. Yeah, this just kind of illustrates the different things. So you can specify, we have a timing graph, right? It's from nodes and edges. And if we have a fan out from this signal here to all these other ones, we can say, oh, don't consider any path through these edges. And then what happens is it actually puts a special tag on it when it's doing propagation. And when you do the arrival time computation, you go forward through the graph. What it does is it says, when it gets to one of these exceptions, it'll say, I'm actually going to duplicate the table and say one of these tables is through this, and the other one is not through this. And so the way these exceptions happen is you keep adding a tag every time you do an exception, and it keeps duplicating the tables for all the possible combinations of these false paths. So it can run slow also if you do too many false paths in a design, because it gets hard to track. It requires exponential numbers of tables in the worst case. Yeah.
How would you encode that using the one hot case? Like how do you know that?
So to be honest, in most cases, I ignore it. Don't do it unless it's a problem. Then it will consider all the possibilities, which is conservative, right? You're safe. If for some reason you go in there and you run your timing, and it has this case where all the one, if you look at your critical path, all the bits in your state have to transition to 1 at the same time for this to happen, then you know it's false. Then you can actually go in and say, you can do an exclusive command too, which I don't think I said. Is you can say, this input is different than this input. You can say signals are mutually exclusive. I don't actually remember what that exact command is, but I've never used that one, to be honest. It's usually things going through those cases I showed, the bidirectional bus or a non-sensitizable path. And the non-sensitizable paths usually happen with reset signals or enable signals or test mode signals, kind of these signals that go everywhere, and so they define certain modes of operation. So it's not really like a signal for one path that you're worried about. Yeah, and so this is just illustrating the tag tables. So if you go through here, this is the same example I did in prior slides on static timing. Remember we had that minimum path going through the top logic and a path going through the bottom logic. And if we actually had, this actually was a false path. And if you look at it, I don't want to go too much into the example, but you can see that it duplicates the tag, or the delays going through that top branch, so that there's two tables for the minimum delay. One is if it actually comes from input B, and the other one is if it comes from the other top input. And if one of those is invalid, then you use only the other one. So I don't want to kind of go into too much detail. Now, there is another thing you will run into with clock domains. So I mentioned at the beginning you can have multiple clocks. On average, a typical chip will have I think the number is 70 clock domains. Right? You have all your different interfaces, USB, on-chip, off-chip, I/O, analog. They get very complex. And in this case, we might have a common thing they do on most chips is the data path may run, actually they run them at twice the clock frequency of the CPU now. This is showing an example where you may have your data path run twice as slow, so it can do more in that cycle. Think about it as like a pipeline with shared, it shares across both stages of a pipeline, right? Well, if you do something like this, you may say the inputs change at a 10 nanosecond clock, but they're only going to come there every other cycle. Or you have to have a buffer that says buffer 1 if 2 come at the same time. So that flow control has to be done logically at an RTL. But assuming sometimes you get one input on a 10 nanosecond clock, you have 2 cycles of that clock to compute the result. And it flows through this in that time. So what you would do here is you create 2 clock signals, one with a period of 20, one with a period of 10. And this is an example of how you can show the waveform. So this is showing that the input is a tuple in Lisp. So it's the curly brackets. The 0 means it transitions the first high, I think, on the first at time 0. Then it goes low at time unit 10. And so we can see the other one goes high at 0 and low at 5, which is the halfway through the period. And we just name them convenient names like clock 10, clock 20. So you want it's often better to describe the clock in the signal name than to just say clock 1, clock 2, and so on. And then you can specify a relationship with that, very much like the false path. So you set multi-cycle path, you get a number of cycles too, and you say it's a setup time, so the long path, from the launching to the capturing. And that then says it'll do static timing through this FPU with twice the amount of time for computing my required times. Right? Instead of using the 10 nanosecond period to compute the rats here, you use the 20 nanosecond time. And then but then the propagation forward behaves just like normal, the propagation backward behaves just like normal. So it's essentially overriding a lot of the other things. Yeah, and then multiple clock domains. This is one of the things where I wish we had more time, more classes. I think people are going to get more experience with this in the capstone when you start actually implementing designs. If you have 2 clocks, I used to teach more in this class too, but obviously there's too much material already in the class. But basically you need to we have data going between different clock domains. You have to either make sure that you have to make sure it's reliably captured. And to do that, you either have to synchronize something that is not in the domain using a number of different techniques. You can use double flip-flops to basically get rid of metastable states. You can use asynchronous handshake synchronizers to basically make sure that the signal is reliably communicated. You can have a FIFO to do mismatch between bandwidth. In that previous example of the FPU, these might be different domains because you might have a FIFO here buffering up things that need to get computed. So there's a case where you might actually have a clock domain cross. You do have a clock domain crossing, and you might want to consider it in special ways here. But there's actually a really, really good paper that I recommend people read. I can put it in the Slack if people are curious. It's by Clifford Cummings. Or I forget if there's a G or not in his name. His name's Cliff. He's basically a consultant, and he does a lot of these things in what's called the Synopsys user groups. So it's basically users of synthesis tools. But he's done a number of papers that are kind of just, over the last 30 years of Verilog design, have been very transformational in the industry. One of them was kind of back when Verilog was new, what is synthesizable Verilog? He did one of those papers. Another one he has is on clock domain crossings. He goes over all of the different techniques in a very accessible way. So if someone reminds me in Slack, I'll put that there. I recommend reading. I reread it recently, and I forgot how good it was. So now one other thing I mentioned before is also the idea of propagated clocks. So we talk about clock skew and how it can affect our timing constraints, right? Well, in order to get clock skew, one thing we can do is propagate the clocks to get the skew. The simpler thing, there's actually 3 different modes of clocks in tools. One is to assume ideal clocks. This is the case where if I give you a problem on exams and in your homework, it's probably assuming ideal clocks, unless I say otherwise. That means all clock signals arrive at the same time, there's no skew. That doesn't happen, that's utopia, right? It never happens. The other approach is called clock uncertainty. This is a simplified approach where you can say, I'm going to assume my clock skew is 30 picoseconds between every pair of flip-flops on my chip. They'll frequently do this. So they'll frequently do the first one when you don't even have placement, you don't have wires, there's a lot of unknown stuff, and so you're just going to assume that because it's good enough. However, let's say you do placement and you know your wires, but you haven't done, or you know your rough wire lengths, but you don't have your clock tree done yet. You don't know if you're going to have skew or not. Well, you might say, I'm going to later design my clock tree and I want it to have less than 30 picosecond skew. So I'm going to do my optimization now, assuming I can do that with my clock tree. It's kind of the look-ahead approach, right? So you're going to say, on this clock, set 30 picoseconds of skew. And it's going to then assume every pair of flops has that 30 picoseconds. It's like you're setting an upper bound on the skew for all possible paths between all possible flops. It's good because it's a single number and it's easy to compute. The third approach is this, propagated clocks. After you know your clock tree, you then know the actual buffers and wires to each flop of the launching and capturing flip-flop. So then you know your delays, you know the exact skew. Once you know that, then you can do your setup and your hold time stuff like we did before, right? You can set the launching times and the clock to Q delay out of the launching flop based on clock I in this case. Then you can set your required time and the setup time on the capturing flop with clock J. So it includes the exact skew. Now, why don't we enable this always? I mentioned before you may not have a clock tree yet. You may not have the wires yet, so it may just be unnecessary at certain points in your design. But after clock synthesis, you typically turn this on, so then you're doing optimization that's aware of your clock tree. Now, this then adds this is kind of an advanced topic, but it's important to know. And then after this, I'm going to then do the demo. So let's say we have a clock tree. And by the way, this is actually a picture from my thesis defense from many decades ago that I still use. So I did variation-aware clock distribution, like how to deal with variation in clock trees on chips. Now let's say we are looking at our design and the launching clock is slow because maybe we're doing a corner and it's slow, okay? And we're doing another corner and let's say the capturing clock is fast. So I talked about corners way back when I talked about libraries and stuff. But let's say we're assuming our launching clock is slow because it's 100 degrees and our capturing clock is fast because it's cold. Now what is the temperature of that root buffer? Well, it can't be hot and cold. It's either hot or cold, right? Now, if I were to assume that it's hot for my launching clock and cold for my capturing clock, I'm assuming double the pessimism. I'm assuming a condition that can never happen. Well, that's a problem. And that means I'm being overly pessimistic when I don't need to be. And so what this does is that shared thing is what's called common path pessimism. And same thing can happen in the other case, where I have fast on the launching clock and slow on the capturing clock. Right? This one is bad for late paths. This one is bad for early paths. Remember, this is just positive or negative skew depending on the setup or hold constraints. So that's kind of a review point. Now, sometimes this can be actually useful skew. So here's a case where I think the next slide is. I didn't have the path. Okay, here's the slide I wanted. So common path pessimism is basically the removal of that shared pessimism, so that root buffer or set of root buffers that can't be both worst and best case. Now, the reason this is challenging is you have to do it on a path-by-path basis. You have to know which flop launches it, which flop captures it. You have to trace up the clock tree and find what part of the clock tree is shared. And then you subtract it away from your skew. And so just like false path enumeration and kind of proving the path is slow, that is also slow. So it's typically only done at the very end of static timing when your design is mostly finished. And there's actually options. Synopsys tools, you set this variable. It's called timing remove clock reconvergence pessimism. OpenSTA has another variable called STA CRPR enabled. The acronym is similar meaning. CRPR, one of them was at IBM, and one of them was everywhere else. That typically happens a lot in industry. IBM used VHDL, everyone else used Verilog. So it's like IBM was a bunch of, a foreign company with a different language in the US. But so this process is what does that. It looks at every pair, removes the overlap of the clock tree, and subtracts it away from your critical path timing. So it's not part of your slack. I'm going to show you how this works actually in the demo. Now, we also want propagated clocks because sometimes this can do what's called useful skew that can actually help us. We already saw that in some of the examples of setup times that if you add additional clock skew and delay the receiving clock, that gives you extra time in your period. So that can actually improve your cycle time. Or if you have a hold time violation, you can actually skew your launching clock later. That'll help your hold time because it launches later, so it gets to the receiving clock later than you want, and that can also benefit your design. Useful skew is the idea of what if I can tune my clock tree just right so that it actually helps everywhere. The problem is that here's kind of an extreme example of if I have a pipeline stages here, and this is some sort of a state machine with pipelines. So there's kind of 3 logic blocks, 3 flip-flops, but there's feedback. And here, if we have delays like this, this is 4 nanoseconds, 2, and 6. What we can do is intentionally skew these 2 clocks over here by 2 nanoseconds, such that it effectively transfers some of this delay over here, so that we can actually run faster. So instead of being limited by that 6 nanoseconds, we launch that B clock earlier relative to the other ones, so they get the head start through the 6 nanosecond logic cloud to get to the C flop early. And that can improve our design. We could then potentially run this at a 4 nanosecond clock period, because we had intentional clock skew between these 2 side buffers and that 1 launching buffer for B. This is included in static timing for free. Like, this is why you turn on propagated clocks, because this could happen and you could get benefit from it. So skew is not always bad, is another point. It can help you sometimes. But in this case, what if you skewed it even more? Well, there's a limit you can't go beyond. If you have a cycle like this, the summation of the cycle divided by the number of stages in the cycle can't be greater than your period, right? Because if it's greater than your period, one of them is going to violate. So there is a limit to how much of this borrowing you can do. Now, I mentioned before with libraries, but what are timing corners? We talked about gate delays. We characterize gate delays at different temperatures, different voltages, and fast, slow transistors typically, and then possibly even old, new transistors. But we also can have process corners related to wires. So when we do our deposition of metal and our planarization during mechanical polishing, we may end up with wires with slightly different sheet resistance at different parts of the chip. This can result in variation. The same wire on a different part will have a different delay. And so we have to look at kind of worst case corners, which are early times want to use the fastest set of variables, late times want to use the slowest set of variables, but you don't want to assume all of them are bad at the same time because then you're extremely pessimistic. So the question is kind of how do you do that? In modern designs, we've already seen the number of corners for the gates, but typically every metal layer will have at least a fast and slow corner. So if we have 14 metal layers, how many combinations of corners are there? 2 to the 14. Right? That's a lot of different corners. You can assume metal 1's fast, 2 is slow, 3 is fast. Every possible combination. The naive assumption, and what you generally have to do, is run actually static timing in all of those corners. That gets rid of our linear time assumption now, right? We do a linear analysis of one of the corners, and now if you do an exponential of them to get the actual answer. That's a problem. Yeah, and so what are fast and slow wires? This can be a little vague. It could be low resistance, low capacitance, but sometimes there's also interaction. If you make a wire thinner, the resistance might go up, but then the coupling capacitance goes down. So it's not necessarily an isolated effect. So it's hard to define whether they're fast or slow. And then the dielectric between wires. If you make it thinner, maybe the dielectric between it and the next layer is thinner, so there's more coupling. The extraction deck will usually have to do this. It'll take the possible conditions and extract the different corners for you, and then you get the different wire extractions for each corner. Here's an actual example of a design. Again, this was from my thesis, but it was something that happened when I was at IBM. In one of the early Sony PlayStation chips, you can tell it's old because PowerPoint degraded and the clock here looks not like a clock anymore, bit rot. But basically they had a problem where they had a critical path, and here I kind of label all of the wires in the clock tree and in the data path. Right? The clock tree is usually on metal 4 or 5 high levels, goes to these buffers. The local stuff is usually on metal 1, 2, 3, and local connections. And what happens here is, at that time, IBM said they only looked at really 2 corners. All my metals are slow, all my metals are fast. Until they ran into a problem. There was something like this where they had basically metal 4, might be used on the root branches here and kind of local here, metal 5 here, and then local here. And what happens is, let's say for setup time, you want to have your capturing clock be as early as possible. And so for that case, you want M5 to be fast. Well, M5 then also changes this launching path to be fast because it's the clock path over here. So they interact. But then M4, if you make that slow, let's say, it might make the capturing slow, which could be good or it could be bad. So the point is, it's not best to assume they're all independently good or bad. It has to be the combination of them that can affect your design. And then my thesis, what I actually did clock construction considering the data path, where I said, I actually modeled as a linear system the delay of basically paths using what's called statistical timing analysis. And so if I could model the data path and say, this data path is highly dependent on metal 5, well, maybe I want to make my clock tree out of metal 5 also to actually cancel out the variation. And that's kind of what my thesis was. Because if they're both out of metal 5, if one goes up, the other goes up too. You're good. So it actually uses correlation to actually improve designs overall. Yeah, and then let's talk about the timing corner explosion. I already mentioned what they typically do in industry is they try to take a representative set of corners. What does that mean? Depends. There's no clear answer. They might take, have 4,000 corners and pick like 30 of them. Say these are the ones that we think are the most important. There's really not a good answer here. This is still, the more corners the better because you have more coverage of the worst case, but it's impossible to do all of them. Now, I'm going to do my demo now, and then I'm going to go and talk a little bit about statistical timing if I have time. I like to talk about statistical timing stuff because that was my thesis related to that, but it's not, no one really uses it in industry too much. It's related to this corner stuff, and so that's why I often drop it from this. But we're finding that everything old is new again. This all happened like a couple decades ago. It's probably going to become more important again very soon. I've been around long enough that I see these patterns in industry. So actually, we are starting to see it because with machine learning, they're trying to do machine learning modeling of the statistical stuff. So there actually are people starting to do it that way. Let me just close out my Slack and stuff. Okay. Okay, what I'm not going to do is I'm not going to talk much about the open road. We're going to use the open road tools for the static timing analysis stuff. In your last two homeworks, you're also going to use the open road tools, but they're part of the tiny tape out setup, which means they get run in Google GitHub Actions. So a lot of the stuff's going to be run automatically in the cloud when you submit your design to GitHub. But what I'm going to do here is run static timing manually, and you can actually, it helps you understand what results you end up seeing in the results on the GitHub cloud runs, right? Because you have to debug that. And sometimes if your design's not working, you can also run the tiny tape out GitHub Actions locally on a machine and do the same stuff. Because also I think people might, if they get a big design, they might run out of they might overgo the time limit for the actions. You might have to run it locally. So, but we'll get to that when we get to it. But here, it uses Docker, and there's a whole tutorial on how to set up this. And I have this script here that is in the Docker tutorial. Let me see if, actually I'm going to pull this away because I don't know what tabs I have open. I don't want my grades, the regrades to be open. Someone, sure. Oh, it's actually your midterm too. So. Okay. Okay. So again, you've seen the chip tutorials. If you go down here, you have to install Docker, which a lot of you probably already have. Then there's the Open Road Flow Scripts installation. What I did here is I cloned this repo. I go into this directory, and here's the script I'm using right here. So I just made a bash script to run all this stuff, and this will run it in Docker and set your display also, so you can actually do X11 stuff and nice things. And then you can also check out different versions. I'm actually using this version here, but if you by default, if you run this, will be the most latest version of Open Road. And I haven't tested my tutorial with that, so use this one for now. Now, if we go into here, so here's the repo I cloned, and then there's that script. So if I want to, and then in this directory, I made a demo, and I'll give this demo to everybody. I can add this on Slack. It's actually 3 files. If we look at this, this is the design. So it's basically a simple module with a clock, an input A and B, and output Y. And I essentially have a clock tree in here too. So I have this kind of a bunch of buffers that buffer the clock in different lengths, because I'm going to demonstrate clock skew and useful skew and propagated clocks versus regular clocks. So you can see these kind of doctored up clocks. Here is one of the flip-flops for A. Here's the other flip-flop for B, and here's the capturing flip-flop for the capturing flip-flop down here. So that's what it is. It's basically 2 inputs going to flip-flop through actually a chain of inverters with a skewed clock, essentially. Now, here I have the commands also from the static timing tutorial. So if you go to the static timing tutorial, down here, static timing analysis, I have actually multiple pages of tutorials. And I spent quite a bit of time on these a while ago to explain stuff. It's, again, kind of the most useful things to know from static timing. It's very complicated, but these are kind of the ideal things. It's the same stuff that applies to industry. So I highly recommend this. I also had that PDF to read about the theory stuff. That is also important, but here's kind of the hands-on tutorials. Now, this assumes that you have a design that I give you called in this final directory, and it also needs the PDK. What I would suggest you do is copy those to the same folder we're going to do the Docker stuff in. So I actually put this, I cloned Open Road Flow Scripts into this ORFS directory, and if I go up to, this is Open Road Flow Scripts. If I go into this directory, this is all the Tcl scripts. I'm actually going to go over some demonstration of Tcl stuff. That's a language I use to program it. And then here I made my demo. So now the reason I do that is because it's in Docker, this flow directory gets exported to the Docker, so that's then in the Docker file system. So just to simplify mounting stuff, that's what I did. So I put it in there to make it easily available in the Docker. So let me run the Docker image. So and I'm going to run it with that hash. Oh, it's been a while, because it was out of here. Okay, let me copy and paste it from over here. I don't remember what the hash was, so. Nope, wrong one. So if I do that, it ran Docker. Don't worry about this error. I'm now in that Open Road Flow Scripts directory, and it mounted the flow directory under it. So if I go into here, that demo script subdirectory is also there. That's my trick to getting things into the Docker image. Here I also put the Sky130 library just for convenience. In most systems, it put it in your PDK root. And so here, I'm going to set PDK root equal to my current directory. So that's how it will find all of that stuff. Now, here, and then once you're in the Docker, you have to also source this in setup file, which adds OpenRoad to your path. You have to do this every time you run the Docker image because it doesn't remember your settings in your environment. So if now I'm in here, so now I can run OpenRoad. Right, there's just the help from OpenRoad. Now, the static timer is part of OpenRoad. So OpenRoad is actually the placement tool, the routing tool, the floor planning tool, clock synthesis, static timing, everything, all in one. You can run it in a GUI mode, like this. It'll pop up a GUI. And this is in some of the tutorials. So I'm not going to go over too much of this. Now, I'm also not going to run the design I just did in this GUI, because if you notice, it was just a Verilog netlist. It didn't have a placement. There was no placement to it. There was no routing. So if I do that, it'll just be blank. I'm just going to do static timing analysis on the gate level netlist only, which is fine because this also just outputs the reports in basically the same format. So if I go in here, flow, demo. Is that big enough for people to see? Hopefully. OK, so now I can run OpenRoad. And you can actually pass it a tickle script as an argument. What is this tickle script? Oops. That's why I don't like it. So here's my demo in another tab. So here's basically the commands in the static timing tutorial. Here's how to read a library file. So read lib. And you can see here it uses the environment variable for that PDK root, which is my current directory. And I'm going to run it with this corner, actually. Typical, 25 degrees Celsius, 1.8 volts. Here are the left files. These are the, now there's actually two left files. This first one is called a tech left. Now the reason I read that is that has the information about the wire, the interconnect stuff. It has my interconnect resistances, capacitances, the layers. The lib file only has the cells. So this tech left has all the information about my routing stuff. And then this third one is the actual abstracted layout of all my cells. So the lib file had the power and delay models. This has the physical layout of the cells, the pins. It doesn't have the transistors in it because that's only in the GDS, the layout, but it has the metal blockages and the pins, essentially. Now what I do here, I can read a design. In this case, it's a Verilog file. There's a number of other formats you can read. You can also read what's called an ODB file, OpenRoad database. Once you start to have placement and routing information, it's easier to read those files. But in this case, it's a text file edited, so it's easy to see and read it. Now, this command here is similar to most tools. You link top, or link design top. The top module in my Verilog is called top. And this basically says to make sure that everything exists in that thing. All the gates I use, all the instances, they all exist. If not, it'll report something is missing. Then I set my design to the top module, and now I read this SDC file. So as you remember, this is Synopsys design constraints, but it's an open standard that everyone uses for their static timing tools. This includes the create clock commands, the set input delay commands, and so on. So let's look at that. Gate level SDC. So here, now this is Tickle, TCL. It's called tool command language. It's worth knowing. I don't write Tickle. It's a scripting language, right? You're going to see jobs that say, oh, we need someone to know Tickle. In reality, when you run a tool, it will frequently output its logs in Tickle. So you can kind of learn by example. That's the case I've mostly seen. There are some very advanced users that write stuff in Tickle. Most tools will actually do a lot of like parameter checking in Tickle. But the advantage of Tickle is it lets you write code in C or C++ and then make new commands in Tickle. So it's that's why I can create a command. Create clock is a command right here on line 6. That is not a normal Tickle command. If I were to just run a Tickle interpreter, it would not know what I'm saying there. But when I run OpenRoad, OpenRoad is using Tickle as an interface. And it says OpenRoad makes a command called create clock. And when I call create clock, it calls the C++ code in OpenRoad and passes my Tickle arguments to that. So that's why Tickle is used on so many EDA tools, because it is a scripting language everyone can know, but then you have to kind of just know the specialized commands for the given tool set. So here is an example one. There's a lot of standard stuff. Here's an example of setting variables. Tickle is a very verbose language. I can set a variable called clock name to CLK, a string. Actually, let me do some stuff in a shell. So if I run OpenRoad, I'm now in a Tickle shell. And if I were to say set, what did I say? Let me keep this here and I can do some of this stuff. Actually, I'm going to first source this so it loads my design. So first thing I'm going to do is source read gate level .tickle. It ran all those commands. And now I have my design in memory. There's a couple, I guess a warning, but a warning in this case is okay. Now, how do I know it works? Well, I could run a Tickle command. I'm guessing this one is. No, that's actually not right. Here's an example. There's a command to report stuff about your design. I don't remember what it is. It said right there's two commands. I can use the help to actually get help on commands. I can go help, asterisk, report, asterisk. Here's all the commands that have the word report in them. I don't know if I can, yeah, I can't do anything like that. If I do this, I can scroll backwards, right? So here's a bunch of commands, all report. Which one do I want? I guess report design area is probably what I want. See, so it's 144 micron squared, 100% utilization. I actually didn't define a floor plan, right? So it just assumes 100%. There's probably options for that command. Like what is report? Nope, there's no options for it. Now, let's get to some Tickle. So I mentioned the variable thing, like I can do set clock name clock. It's set it. I can also then treat it as a variable. What has clock name? It prints. Everything in this is a list. So if I go set, before we saw waveform, I could do it like this. That set waveform as a variable that was the list of integers 0 and 5, right? What if I put that? I don't even know. Yeah, I just put it out like that. But it's not a string, right? If I set it as waveform, it look very similar. But the point being, it can be strings, these can be lists, these can be integers, these can be floats. I actually think floating point requires special arguments. I think that might actually be a string stored as a float, but don't hold me to that. Now, when I run commands in Tickle, like let's say I go through these SDC commands. If I want gate level SDC. So I ran these two commands. So this one sets the clock name, then it sets clock port. And in here is how we can run a command in Tickle. So what do I mean run a command? So it called set clock, which set that variable, and then it set the variable clock port. Now brackets executes a command in Tickle. So it executes a command, and it's called get port. If I type help get port, oh, yeah, it is a command. It's just not in the help for some reason. But it then gets the port of my design with that name. So I have an input to my design called CLK. And what it did, this is a useful point, is it executed that command, it returned a value. This is actually a pointer to the C code. Right? This nasty thing, that's a pointer. It's a pointer to a port. A port is a C++ object in the code in OpenRoad that I can then do stuff to. What if I print that? Like if I print it by default, it just outputs that string which says, oh, it's an object. Now, how do I use that? Well, I can pass that to other commands in OpenRoad and say, do stuff to this port. So this is why Tcl is such a useful thing. Is if I wanted to print details about that, I'd have to use one of their commands that knows what this is to be able to print that information. You can't parse it in Tcl itself with the native Tcl commands. So what do I do with that next? So here, I'm actually going to define create a clock on that port. So here's an example of, oops, cut and paste didn't like that. Ah, oh man. You can also put Tcl scripts on a command line, and I don't know why I didn't like that over here. Here it's better. So now I created a clock called clock name, which was the previous variable on the port that I just returned, and I gave it a period of 0.8. So I have a clock defined in my design. Here I'm going to also get the clock, right? So here I set this variable clock, and I retrieve the clock from OpenRoad, get the clock called clock name. And then I can set the transition value on that. So set clock transition, this is the rise and fall time of the clock. So it's not a perfectly square clock, it's actually got a 0.1 nanosecond slew rate on the rise and falls. Now, here's some other stuff I can do. There's a command built in from OpenRoad called all inputs. That is, it returns a list of all of my input ports to my design. In this case, there's 3 of them. If you remember, they were A, B, and clock. I don't know which one's which, right? Because they're in memory in C++ land. But what I can do here is, this next command is actually going to find which one of them is the clock. And it's going to execute, for example, a search command. This lsearch is a list search in Tcl. It's going to use that same list. Actually, I could use the list from above as well. And it's going to look for the clock port in that list. And then here it's going to replace that index with nothing. So this essentially removes the clock from that list. So if I do it over here, now I have a list of 2 things and an empty thing on the end, which was where my clock was. Why did I do that? Well, this is a scripting way of setting now. If I go down here, I can also do the same thing for my outputs. In this case, there's one output, it was Y. But it's just in C++ land. Now, why did I do that? Well, here I want to set my input constraints. Remember, you do that with set input delay and set input transition. So it defines the delay on the primary input and the slew on the primary input. And here, I apply it to all the inputs without the clock, right? So A and B. So this is a useful script you can reuse a lot of times, where it can do general constraints for a design with any number of inputs. Otherwise, you have to go through and type, set input delay A, set input delay B. A lot of scripts will build on things, and you'll provide exceptions if you don't want these, but you'll have a blanket set of constraints for your design. So there, I have input constraints. Now I do the same thing for my outputs. I set my output delay and my output load. Ignore this down here. This is just for demo purposes. What I do in this design is I ignore actually the primary inputs to the D flip-flops and from the D flip-flop to the primary outputs, because I only want to consider flop-to-flop paths in this demo. So that's why I intentionally did this. You would not do this in a real design. Okay, now my design's loaded and I set my constraints. What do I do? There's a command called report checks. This is the main command in OpenSTA. It looks like this. Here's an example where the help is actually useful. There's a lot of stuff. Remember the things I said about false paths. You can actually apply the same ideas and say, I want to report only timing checks from these points, to these points, through these points. By default, it'll do all of your design, but you can actually limit it. There's a few options in here that are pretty useful. In particular, if you have multiple, this path delay defines what type of paths I want to look at. Minimum are your hold paths, maximum are your setup paths. Or you can also look at your minimum rise and fall, the ones with the word slew rather than the timing. You can also change the format. I'll talk about that in a minute. And yeah, we'll keep it. And then this path group can also be useful sometimes. But if I just run report checks by itself, it does this. So what did it do? Here is a timing report in static timing. These are very similar to every commercial EDA tool. They were carefully crafted to not be exactly the same because copyright stuff. But by reading this, you'll be able to understand other reports too, because they're also quite similar. Now, here you can see at the top, this reported a start point. This is the launching point of my path. And you can see it's ADFF. That was the input, primary input went to a DFF. It was called ADFF. And then it goes out to some logic. And then the endpoint is YDFF. And then the output of the YDFF went off chip. But remember, I'm only considering the 2 flip-flops to the Y flip-flop, and I ignored those input and output paths. Now, the path group specifies essentially the clock domain. This is in the CLK clock domain. Path type, it's a setup time path. Why did it do that? I didn't give it any arguments, but it picks the worst. Actually, it picks the worst by default. Now, what does this look like? Well, if I scroll back a little bit, let me get this all on the screen. So we see that header information that describes what type of path it is. Here's my actual path now. And this is where everything is in text reports. You run this on a machine. If you run static timing, it takes hours, days to run. You get back a report. That's why in industry, they don't really look at the GUI for this stuff because it's a batch job. Your GitHub action is going to be a batch job. It's going to run. You're going to be able to click on the final GitHub stuff and see these reports. You can't load it in the design and point and click different parts of your design. If you ran it in the GUI, you could do that. But it's in practice, it's not as useful. Now, what does this look like? Well, I can see here's the launching clock. Oh, if I went back up a little bit more, it was from the rising edge trigger D flip-flop clock by clock. And it goes to the rising edge trigger flip-flop clock by clock. That could be a negative edge triggered flop. It could be an input or an output. It could be a different clock domain. It's important to see what caused these launching and capturing values. But if I scroll down here now, I can see here's the start of my path. It's going to start at the clock of the launching flip-flop. So clock CLK rising edge at time 0. Here, notice this. Clock network delay ideal. Oops. Ideal. This has ideal clocks, no skew. So this it's not turned on. Remember I showed you the Verilog, it had clocks in it? They're not turned on in static timing right now. So I'm going to turn them on in a bit and show you the difference. But here you can see this shows you the rising edge. So this caret shows a rising edge and a V shows a falling edge. The rising edge of clock causes a falling output on Q. So this is where rising and falling matters. The worst delay path from this is the falling output of Q, not the rising. And then it goes through the rest of the stages. And here you can see it goes to this flip-flop, this inverter I1, I2, I3. There's 8 inverters. You can see the cell type here. They're all Skywater inverter ones. It goes rising, falling out of the flip-flop, rising on the output of the first inverter, falling, rising, falling, rising, falling, rising, falling. And after the 8th inverter, it goes to an AND gate, an AND 2 gate. and it goes to the, you don't know which input pin of that gate, but you see the output pin here of that gate. It's the falling output of that AND gate. And then it goes to this capturing key flip-flop. Now, the nice thing is this shows on the left column your delay of each stage, and then in the time column, that's the cumulative delay of your path. Right? So you can see, what is the slowest delay of my path? Well, it's actually the clock to Q delay, 0.33 of my launching. Everything else is about 0.04, 0.03, and then this AND gate was a little slow too, but it's not really big compared to the launching of flip-flop. That's what you can do. Then you can just see the accumulation of that time here. And then the data here arrives at the capturing flip-flop, D, at this time, 0.69. Now, what if I keep going down in this? Now I separate, now that I did the end of the data path, this is my capturing clock on the final flip-flop. Notice here, it's the setup time. This is the setup time of that flip-flop, 0.8. It puts it in there. Or sorry, this is, no, sorry, no. It's an ideal clock, that is the period. Remember, I defined my clock period to start, 0.8. It does not have the setup time yet. There's actually no clock network delay because it's an ideal clock. Remember I told you clock reconvergence pessimism? That's turned off, so that's also 0. But that is a line in here. And then here is the rising edge of that capturing clock at 0.8. Here's my setup time. Library setup time, 0.09. It's actually a negative setup time for this flop. You can have negative setup times. What that means is the input to the flop can arrive a little bit after the clock and still be captured. It's mostly due to internal delays of the path inside, meaning that the clock is probably buffered inside the flop. So the actual capturing is by a buffered clock, which makes it look like the input can arrive later. So we have the library setup time, and then we have the data required time, which that is basically subtracting the setup time from the clock period. Now, data required time, data arrival time, subtract them, and you end up with the slack. Wrap minus hat, slack. We have 0.02 slack. It meets timing. This is all good. Right? Positive slack. This includes the subtract for the negative in there. Right? Pretty neat, right? Well, let me turn, I have a couple things I want to play with. So that assumed ideal clocks. Actually, let me select this. Here's some commands I have in here. This one sets clock uncertainty to a constant value. So I just turned on clock uncertainty of 0.1 nanoseconds, and that's going to assume I have skew between all pairs of my clocks. What if I rerun report checks? Here I have a violation now. First thing to notice. Violation, negative slack, 0.08. I did not meet timing. Clock skew caused a problem. What if I scroll back up here and kind of look at why? Notice I still have the same launching clock. All this stuff is actually the same up to 0.69. The constraint here is the same. But I added this clock uncertainty of negative 10 to the capturing clock. Remember, it's a setup check. If my clock arrives early, that's bad. So I subtract off that uncertainty on the setup check, and that determines my capturing clock. Then the setup time's the same, and so on. So basically, this is, because of clock uncertainty, it's 0.1 nanoseconds more constrictive. And instead of 0.02 positive slack, I have negative 0.08 negative slack. Right? So you can see. Now, what if I want to do, oops. I can look at minimum path too. Actually, let me turn, how do I turn this off? Is there unset? Sometimes things aren't easily unset. Yeah, it did. Let's see if that works. Okay, I'm back to the 0.02. Now, what if I want to look at the minimum path delay? Here, I intentionally made this example, so one of the paths from A was through 8 inverters. There's another path through B that goes through 1 inverter, and then the AND gate. Here's my short path. So I just specified do the minimum check and go here. And so you can see it's same stuff, launching path. Launching clock goes through all these paths, 1 inverter, the same AND gate, but the other input, and it gets to the data flop, and it's 0.48. The other one was 0.69, I think. So it's much faster through this path. Clock here, I turned off the clock skew, so it's an ideal clock. The hold time's also negative, but it's this hold time. And then here you just want to make sure that the data required time is, the arrival time is later than the required time. And so here I have positive slack. Now, I can also turn on clock skew here, do the minimum path. Same idea, it changes a little bit, except now look, that slack actually helped me. It meets timing there. That's interesting. Why did that do that? What did it look like before? I wasn't making note. Oh, it met before by 0.5, and it still meets timing by 0.4. So the margin is less, but it's still okay. The skew is not problematic for this whole path. Now, what if we go in here and instead of that, here's one where we can do set propagated clocks. That means I'm going to actually use the actual clock tree rather than that uncertainty value. Let's go through and do report checks. And here I got another path. This is from A to Y, same thing. The main difference here is it has this, oh, I had uncertainty in there still. Let me turn off the uncertainty. The uncertainty adds to the clock skew. So if I turn this off and run this, here I have the propagated clock network delay. Actually, I also have the propagated at the top. Let me go up there and look. So here, the input to the chip is at clock, but then there's network delay to the launching flop of 0.19. This is when the clock arrives at that flip-flop. If I look down here, here's the capturing clock that's a period later. The clock network delay propagated to that is 0.18. It's a little bit quicker, 0.19, 0.18, but they're not equal. And it does the same check. Remember, if we had positive skew with ideal clocks, this is still less than the margin we had, so it's still okay. So clock skew did not cause a problem with the actual clocks in this. Now, what about the minimum path? That's also okay. We look at that. So this is with the propagated clocks. Now, there's actually another thing here. You can, let me remember what it is. There's another mode where you can do report checks minus format full clock. This actually shows me a little more information. Like here, it actually shows me the gates along my clock path. Here's the input to the clock. It goes through 1, 2, 3, 4 inverters, clock inverters, before it gets to this clock. So it kind of prepended that to the path, rather than the last one I just summarized it as a delay of 0.19, I think it was. Same thing with the capturing down here. That also goes through 4 inverters before it gets here. So that's one useful thing. You can report that. There's another one. What if I just do full? No, it's not full that I want. I want full clock expanded. No, it's not that one, which is the one I want. There's another way to get some additional information out of this. Oh, here, it's these, minus fields. So right now it only displays the delay of each stage and the accumulated delay. I can also have it display the slew, the nets, actually, I don't know if they're spaced. I don't know the syntax here. Let me try it. You have to do it each time. Fields, nets. No, yeah, it doesn't do error checking. How do I call that command? Maybe I give it a list. This is what I mean by tickle. It's like I don't remember tickle. There, you get a list of them. So what are the things I can do? I can do capacitance, slew, net are the ones that I find interesting. Slew, net, capacitance. And then I'm also going to say digits. I'm going to go 3 digits instead of 2, so it's a little more accuracy. Look at this now. So here, I not only have the delay at every stage, but I can look at this and be like, oh, is the input slew bad to a given stage? That could be causing the delay. Or what is the load capacitance of the gate at that point? Is that causing a problem? These are all pretty low load capacitances, right? And they're all pretty good slew rates, so they're not a problem. But this is where you can use this to diagnose, what is the issue with my timing? Why is this bad? Maybe one of these had a really bad fan out and had a bad slew and was undersized. You can look at it and see that. Now, I'm going to make 2 more comments, and then we'll call it a day. You can also do one thing here called early rate late, where I mentioned corners, where a corner you have to basically pick a lib file. This lets you set a blanket scaling of different parameters. I can say, I want all my late times to be padded by 10%, just in case. Or all my early times to be made extra early by 10% to kind of exacerbate certain conditions. So that's one thing that people do to approximate some timing corners. Maybe pick one of the corners, make it a little better, a little worse, and then use that. And so but this applies to, yeah, I'll leave that there. It's more the statistical timing stuff that I kind of skipped over. Now, what else about this? I think that's, the other thing I'll also mention, we're going to talk about power the next lecture. There's also a report power command in here. This talks about the 3 types of power, which we'll talk about next lecture. Internal power, switching power, and leakage power. And then it also talks about what is causing that. So here we have the sequential elements like your flops, your combination logic, your clock, your macros, or your IO pads. And so you can kind of diagnose where your power consumption comes from. So I'll introduce that next time, but remember I'm going to show this and you can see where you got it from. Okay.
Thank you. Jason, I got accepted to UCLA. Oh, let's go. Yeah,
one specific wires are different, like different lines.
You can, yeah.
Because I saw the other ones listed like 50-50. I included a 0.6 of those. That one didn't, so I didn't know.